Hi, I'm Shandor Lucky from Edward Loren University, and I'm one of the key architects of a P4 compiler called Tapas. In PEPI, we are using Tapas as the P4 backend. In this video, I will give an insight about Tapas and will show how we can use it in the PEPI platform. Our main goals with Tapas was to create a compiler in which most components can be reused when we move from one hardware target to another. To this end, we separated hardware-dependent and independent parts, and hardware-dependent parts are implemented by a network hardware abstraction library, which is currently implemented for DPDK as well. This design resulted in a multi-target compiler architecture. Given a P4 program, we use the standard P4C2 to generate the intermediate representation. Then this representation is used by the core compiler to create a hardware-independent C code. This C code relies on API calls implemented by the network hardware abstraction library. The network hardware abstraction hardware library is implemented for the given target. So if we move to another target, we only have to replace this component. Then we use standard C compiler and linkers to combine the two components, the hardware dependent and independent parts, and generate the switch program at the end. The separation on hardware independent and dependent parts has many advantages and disadvantages. On the pro side, we can say that we get a much simpler compiler design. Modularity means that we get better maintainability. The network hardware abstraction library is exchangeable, which means that if we move to another target, we only have to rewrite this part and the core compiler remains the same. And finally, the network hardware abstraction library is not affected by changes in the P4 program. On the con side, we can say that this design results in potentially lower performance because there are difficulties with protocol and hardware dependent optimization. The core code is hardware independent, so in the C code we cannot use the hardware dependent optimization tricks. The communication overhead is another issue since the communication is done via C function calls. The core part may be too general, while the network hardware abstraction library is too detailed. The separation between hardware independent and dependent parts should be selected carefully at a given abstraction level. In our case, the hardware-independent part includes header configuration, table configuration, the parser description, and so on. However, the hardware-dependent part implements how table lookups can be done, how tables are implemented and represented, how packets are represented in the given architecture, and all the hardware-related primitives are implemented by the hardware-dependent component. Tapas implements a run-to-completion execution model, which means that the packet is processed from the beginning to the end on a single thread. After receiving a packet, we get standard metadata, which is implemented by the network hardware abstraction library. However, it can be used in the core C code. The packet is implemented in the core as an abstract packet type, and actual implementation for DPDK is done by RTMBuff types. We implement lightweight parsing. It is part of the core compiler. However, the lightweight parse representation is implemented by the network hardware abstraction library, where we store the types, the pointers to the given packet representations and the lengths in bytes or bits. The packet representation, together with the lightweight parse representation, is called packet description. And then this packet description is used by the control blocks and in the implementation of the control blocks. Controls and actions are translated to C functions. Here you can see, when we apply a table, first we have to calculate the keys for the lookup tables. Key calculation is implemented by the core. Then the keys are applied on the given table instances. However, these table instances are implemented by the network hardware abstraction library, and we can access them through some specific function calls. Then, as a result, we get back an action, and the action is executed. The action is implemented by the core, and in this implementation, we can use the primitives provided by the network hardware abstraction library. The network hardware abstraction library is implemented as a low-level generic C API. This can be considered as a layer or as an interface between the high-level C program and the networking hardware functionalities. The hardware-specific implementations include state settings of tables, counters, registers, operations related to these objects. It also includes how we can represent packets and how we can receive them and send them through the different interfaces. It also implements the primitive actions, how we can access header fields, how we can generate digest. And there are lots of helpers for primitive actions to modify or read or write different header fields or metadata. Or here you can see some examples how we can add the new headers, how we can remove headers. There are field modification and extraction macros implemented in C, and there are table and counter operations. As mentioned, Tapas was not designed for PEPI, so generally it can work on standard x86 architectures as well. Here you can see some examples implementing a layer 2 forwarding program, and we compare the result to the DPDK based Open vSwitch implementation. And you can see that Tapas has a comparable performance since Tapas generates native DPDK applications. In some scenarios, we expect a bit higher throughput than with OVS, which is totally reconfigurable in runtime. Okay, currently Tapas is the DP for backend of PEPI. We use two Tapas components. The core compiler, to this end, we created a separate GitHub fork for supporting Raspberry Pi. And the other component is the P4 runtime component, which is implemented by a separate library. And we use this library together with the core compiler to have a P4 runtime server on top of the generated switch program. Tapas currently implements and supports P416 language. We support Viva model. However, there are extra experimental support for PSA. And it supports multiple targets, but in PEPI we use the Intel DPDK implementation of the network hardware abstraction library. There are some Tapas specific settings and limitations we have to mention. The first thing is that we use egress port that can be written in both ingress and egress controls. We can also read them in both control blocks. It is because we implement the run to completion execution model. It doesn't really matter where we set the egress port. So in Tapas P4 programs, the egress path is not used at all. There are some core features in Tapas that are missing, and we are expecting contributions to implement these missing features. For example, look ahead operation in the parsing block is not supported. Meters are not implemented yet. Terminal match kind is not supported at the moment. In the P4 runtime component, which is implemented by a separate library, We only support inserting table entries, reading counters, and generating digest messages. After connecting to the PEPI hotspot and opening an SSH terminal to one of its management interface, we can start a P4 program in multiple ways. The easiest way is to use the Tapas service. To this end, we have to add the name of the P4 program, which has previously deployed on the node, to a configuration file under the root home directory. And then we can restart the Tapas service, and then our new program will start running, and we can connect to it and send traffic through it. You can see in this figure that it first starts compiling the P4 program, and after that the ARP ICMP example starts running, occupying 2 CPU cores. In addition to the Tapas service, we can also run P4 programs manually using the specific Tapas commands. To this end, we first tap the Tapas service and then move to the root home directory. And in the root home directory, we can find the Tapas folder in which the Tapas implementation is available. We can also list the examples folder where we can find the deployed P4 programs. Then, using the tapas sh command, we can launch the specific or the given P4 program. The P4RT at the end means that we want to execute the P4 runtime server as well. Then the switch starts running. And after that, we can also connect to the running switch program through the P4 runtime shell. And for this, we also have a specific helper script. We also have to specify the P4 program which is running, since the runtime P4 runtime files are needed for the execution of P4 runtime shell. Okay, the Tapas script can be launched in verbose mode, through which we can get feedback about the packet processing steps performed by the Tapas switch. To this end, we have to add the verbose and DBG options to the end of the Tapas sh script. After running the Tapas switch in verbose mode, we can see all the packet processing steps that are executed by the P4 switch. You can see the details about the parsing block, which header was parsed, which are missing. You can see the applied lookup tables and the results of the lookup tables, the different fields, including the keys that were used in the lookup tables. Okay, to create a new P4 project in PAPI, we first tap the Tapas service. And we are in the Tapas folder, as mentioned previously. We can go to the examples folder where the deployed programs are stored. We can move our new program here. I simply copy the basic mirror P4 program, and the new program is called myprog P4. You can see the P4 code here. It's a very basic application. And then we also have to modify the examples configuration file. It's in the main folder of Tapas. And here you can see that all the different examples are listed here. We can add the myprog, and we can use the same settings and as with the previous programs. It means that, or it defines that the architecture is DPDK. We use the V1 model, and we use the parameters designed for Raspberry Pi execution. And after that, the myprog is available, so we can launch the Tapas SA script with these parameters, and it compiles the new program. And after that, the new program will be launched. So the compilation takes time. And the generated program has already been executed. So it's up and running. Okay, Tapas parameters are partially set in the examples config file. The last two options in every P4 program defines the parameters of the given DPDK application. And in ops DPDK config file, we can see the details of these two options. The pi-eal are the general parameters of any DPDK programs. The first parameter is the CPU core mask, where our application is running. VDAV defines virtual devices, virtual interfaces, where we use the libpcap Polmo driver. We define two virtual interfaces, and the PyPorts implements or defines the application-specific parameters, how the ports are connected to the CPU cores and which ports are used. For more details, visit our GitHub site, where in the wiki pages you can find several descriptions about how to run P4 programs on PAPI. Thank you for your attention.